All right, here we go with Chapter 9, Homework 2A review. I guess it's called 2A this year. Last one of the semester, so thank you for tuning in. I hope you guys found these useful throughout the course. Average this week was a 9.45 out of 12, so not quite as high as the previous weeks, but still not a bad way to end. And some of these topics will be covered on the final exam, so really all of them will, so we need to make sure that we're clear on them going into this last week of the course. All right, so we'll start with a few requests from students, move on to some of the ones that I identified in Blackboard as being ones we had difficulty with, and we will go through about 10 questions today or so. All right, so the first question, which came from a student, was which of the following pairs is arranged with a particle of higher polarizability listed first? And so I think some of the confusion here was the difference between polarizability and polarity. So we learned a lot earlier in the course about polarity. And remember that this is determined by differences in electronegativity for an individual bond, as well as for molecular polarity, the shape of the molecule. And we have all these rules for predicting which bond is most polar, which molecule is and is not polar, and so on. But when we're talking about polarizability, this is a bit of a different concept. So this has actually nothing to do with electronegativity or bond polarity or anything like that. Polarizability is the ability of the electron cloud to distort. So polarizability exists whether or not the molecule is polar. They have nothing really to do with each other. They're two separate topics. So it's the ability of the electron cloud to distort, and the reason why it's important is that higher polarizability correlates with stronger London dispersion forces. All right, so we said that London dispersion forces are the weakest of the intermolecular forces, but they can still, in some cases, be stronger than others, and so the more polarizable the molecule is or the particle is, the stronger the London dispersion forces are going to be. All right, and generally when we're comparing polarizability, there's two things we look at. So if you have a higher molar mass, that generally means more polarizable. Now really what this is coming from is that you have basically more electrons, and the more electrons you have, the better the ability for these electrons to distort and cause these instantaneous dipoles that lead to London dispersion forces. So that's typically what we look at as molar mass. Now if you have very similar molar masses for two species, if it's more of an overall linear shape, that also correlates with higher polarizability. Whereas if it's spherical, that's going to be smaller polarizability. So the two things we look at when comparing polarizability, as we're doing here, are first look at the molar mass. If it has a higher molar mass, it's more polarizable, and in most cases it's as simple as that. If we're comparing two molecules that have similar or identical molar masses, the one that has more of an oblong or linear shape is going to have higher polarizability than something that's more round and spherical. Okay? So if we look at these ones here, the one with the higher polarizability, we first look at molar mass. So CCl4, CBr4, neither of these are polar, but yet they still have polarizability, and this one we would expect to have larger CBr. So we're looking for the one that has the higher polarizability listed first, so it's not that one. In choice B, we have H2O versus H2SE. These are both polar molecules. Water, H2O, is actually more polar than H2SE, but that does not mean it's more polarizable. And because of the higher molar mass of H2SE, this one would also be more polarizable. All right, so that one's wrong. But then if we look at choice C here, we have two hydrocarbons. Both of these are nonpolar, but C8H18, C4H10, the one that's larger, that has the higher molar mass, is going to be more polarizable. So this one, the first one, is the more polarizable of the two, so that's the answer we'd want to pick. The last two, D and E, NH3, NF3, again, a little bit difficult to compare these in terms of polarity. They're both polar, but which one's more polar is not a simple comparison, but NF3 would be more polarizable because it has a higher molar mass, same shape basically. And then Br minus I minus, two individual ions, again, the one that's larger has a higher molar mass is going to be more polarizable, so that would be I minus. So the only one of these were the more polarizable species is listed first is choice C, so that's going to be our answer. None of these required us to think about the overall shape of the molecule. So where shape of the molecule would come in is, we talked about this in class a little bit. This is sort of tangential to this question, but if we had to compare these two molecules, let's say linear pentane, which has 5 carbons, or if we had to compare that to the isomer that has sort of more of a spherical shape, so not stretched out like this in a line, but actually more arranged in a sphere, this one here is going to have higher polarizability because of the longer shape of the molecule. So these two have the same molar mass, so we can't use that to compare polarizability, but this first one here, because it has the more oblong shape, is going to be more polarizable. So we really only need to think about shape when we have very similar or same molar masses. But all of these here in this question, the molar masses were significantly different, number of electrons significantly different for all of them. So the one that has the more electrons or higher molar masses, it turns out, is the same way of thinking about that, is going to be more polarizable. Alright, the next question also deals with another property of liquids, which is surface tension. So here we're looking for the highest surface tension. So this is one of those many properties that correlates with intermolecular forces. So the highest surface tension is going to be the one that has the strongest intermolecular forces. And this question actually requires us to think a little bit deeper than we have so far, as we'll see. So the first thing we want to look for is, what is the strongest intermolecular force in all of these molecules, and then we want to decide which one is the strongest overall. So if we look at choice A here, this one has an OH bond. This is going to have hydrogen bonding. Choice B here is polar. It has no OH bonds though. So it has carbon-oxygen bonds, but no OH bonds. So this one's going to have dipole-dipole forces, but not hydrogen bonding, because there's no hydrogen bonded directly to oxygen. This molecule here, choice C, is also polar, but it's going to again not have any hydrogen bondings because there's no hydrogen directly bonded to oxygen. So the strongest intermolecular force there would be also dipole-dipole. CH3CH2COOH, one of our carboxylic acids similar to acetic acid, again an OH bond, so this is going to have hydrogen bonding. Choice E is a hydrocarbon, so this is only going to have London dispersion forces, the weakest. So the one that's going to have the higher surface tension is going to be either A or D, and it's kind of difficult to compare these. How do we decide which of these hydrogen bonding interactions is stronger? They both have hydrogen bonds. Both of those are stronger than the rest. So how do we decide? So in choice A, you just have one OH bond and no other oxygen atoms. So when you have hydrogen bonding, this is, again, taking it a little bit step beyond what we covered in class. You have, again, OH bonds here. And the hydrogen that's bonded to oxygen is what's referred to as the hydrogen bond donor. Alright, so this terminology is maybe not terribly important for us, but basically you have a hydrogen bond donor, which is the delta plus. That's where you're going to have interactions with the more electronegative atom, delta minus, which we call the hydrogen bond acceptor. So this molecule here has one hydrogen bond donor, it has this OH here that's polarized, has one hydrogen bond acceptor, which is our delta minus oxygen, the more electronegative one. And so those are how the hydrogen bonds are going to work. You're going to have delta plus and delta minus from two different molecules aligning with each other and interacting. Now if we go to choice D here, which has this structure, we still have one hydrogen bond donor in this molecule, but we'll notice that we have this oxygen here, which is delta minus, so this is going to be a hydrogen bond acceptor. Draw the arrow the other way to be consistent. So we have this hydrogen bond acceptor, but then we also have this oxygen. Even though it doesn't have a hydrogen directly bonded to it, it still is polarized because there's more electronegative than carbon. So this is going to be another hydrogen bond acceptor. So the point is, this molecule here in D, it has one hydrogen bond, one OH bond, but it has two possible ways for that delta plus to interact. So you have more possible hydrogen bonding interactions. So basically this hydrogen bond donor, this delta plus, can interact with another molecule either through this oxygen here or through the other oxygen here. We're always talking about interactions of two or more molecules, but we have more possible ways that this molecule can hydrogen bond with itself, with this partially positive hydrogen interacting either with this oxygen or the other oxygen, so there's going to be a stronger net hydrogen bond because there's more ways for them to interact. So choice D is one that we want to choose here. Even though they both have hydrogen bonding interactions between A and D, in choice D we have more possible ways, more electronegative atoms where this polarized hydrogen can interact with, so it's going to be an overall stronger interaction. All right, so hopefully that makes sense. It did require us to think a little bit beyond how we normally think about these. So even though, as I said, this oxygen here does not have a hydrogen bonded directly to it, it can still participate in hydrogen bonding interactions by interacting with this hydrogen atom from another molecule, and those types of interactions can strengthen relative to just the alcohol here, OH, where there's only one possible way for them to interact. Okay. The next question here deals with the crystal structures of ionic compounds. So we have a metal bromide, MBr, which crystallizes in a primitive cubic unit cell with bromide ions at the lattice point. So it says primitive cubic here. So what we're going to have is a cubic unit cell, and we're going to have, I always do a bad job of drawing that. Alright, so here's our cubic unit cell, and then we have bromide ions on the lattice points. That means we're going to have bromide, I'll just actually draw it in, on all corners. So when we have primitive unit cell, we have just the corner positions occupied. And then it says the metal ion occupies cubic holes. So remember that cubic holes is right at the center of the primitive cubic lattice. So it's right in the middle here. That's where our metal is going to be. I'll draw it as M to identify it as metal eventually. Alright, so there's our metal. And we want to know how many bromide ions surround each metal ion. So if we look, this one's going to be equally surrounded by all 8 corners. So the answer here would be 8 are going to surround each bromide ion. Each metal is surrounded by 8 bromide ions. What this question was really asking for was the coordination number. It's another way of saying coordination number when you say how many surrounded or how many nearest neighbors does it have. And as we said, in ionic structures there's 3 types of holes. So you have, going from smallest to largest, we have tetrahedral holes. And the coordination number is 4. We have octahedral holes, and as the name implies, the coordination number for an octahedral hole is 6. Remember that the octahedral geometry that we learned about back in Chapter 4 had 6 bonds to it, so it's going to be 6 for octahedral holes. And then cubic holes, which is a new sort of nomenclature that we didn't see before, but introduced in this topic. This is one we have here where the coordination number is 8. So these are the 3 major types of holes in cubic lattices that we're responsible for knowing, and one of the properties of those that we want you to understand is the coordination number. So 4 for tetrahedral holes, 6 for octahedral holes, 8 for cubic holes, which is exactly what we have here is a coordination number of 8. So whether or not you can draw the picture even similarly as good as I did, which was admittedly not very good, but whether you draw the pictures or not, as long as you know the coordination numbers of the different ionic holes, that's going to be something that we ask you about potentially on the exam. All right, the next several questions are ones that I found in Blackboard that we have some trouble with. So this question asks about the meniscus of a mercury in a glass capillary tube. So when we're talking about meniscus, that's when we put a liquid into a glass tube and we look at the surface of the liquid, and there's 2 limiting possibilities. So we have this possibility here. So this is, again, the blue is the liquid, and this is the surface of the liquid here. I'm going to sort of exaggerate. And the other possibility is, let me move it over a little bit from here. The other possibility is this. So the surface of the liquid can either buckle in like it does over here or buckle out like it does over there. This is referred to as concave because the surface of the liquid caves in. This one is referred to as convex. All right. And what's sort of going on when we have these liquids inside of a tube, there's sort of a competition between 2 forces. There's the intermolecular forces of the liquid molecules or atoms with themselves, And then there's the intermolecular forces of the liquid with the side of the glass, it's the surface of the glass. So in a concave meniscus, you have stronger interactions with the glass, so the liquid starts to rise up the side of the glass, so that it'll have more contact with the side of the glass. So that's what we see in a concave meniscus, and those forces are called cohesive and adhesive. So in a concave meniscus, the adhesive forces, which are the forces of interaction between the liquid and the glass, are stronger than the cohesive forces, which are the forces of the liquid interacting with itself. And then in convex meniscus, it's opposite. So in a convex meniscus, the molecules in the liquid are interacting with themselves more strongly, so they want to pack together and hunker down like this, and they don't climb up the sides of the glass because they don't want to interact with the glass as much. So in a convex meniscus, your cohesive forces are going to be the ones that are stronger. All right, and we didn't use that exact terminology here, but if we look at the answer choices, the meniscus in Mercury is convex because, so we're looking at a convex situation here, so we're looking at this one. And the first one deals with the density of Mercury, which has nothing to do with the meniscus. Surface tension is sort of a related but different concept, so those two don't have a direct relationship. You can have high surface tension with a concave meniscus or convex, so the surface tension doesn't really play into in here directly. But here, choices D, C, and D, the smaller attraction of Mercury atoms to the glass than to each other, and that's the situation we have with Mercury. So when we say that the attraction of the Mercury atoms to the glass are smaller, that means the adhesive forces are smaller than to each other, which is cohesive. So choice C is basically what we're looking for, cohesive forces being stronger than adhesive. Choice D is the opposite, so that one doesn't work. And then choice E, electrostatic repulsion between the glass and the mercury. We never have any repulsion, we just have weaker or stronger attraction. So there's never going to be repulsive interactions between the glass and liquid. So choice C is the only one that works, which basically says that the forces of attraction of mercury atoms to themselves are stronger than the attractions to the glass, and so that's why we have a convex meniscus. Okay? Alright, the next one here deals with calculations of vapor pressure. So we're again dealing with liquids, and this time more of a numerical approach to calculate vapor pressure. So xenon has an enthalpy of vaporization of 12.6 kilojoules per mole and a vapor pressure of 1 atmosphere at minus 108. So that means the boiling point of a xenon, the normal boiling point, is minus 108 for what that's worth. What is the vapor pressure at minus 148? So we give you that the vapor pressure is 1 atmosphere at minus 108. We want to find it at minus 148. Remember that vapor pressure always increases with temperature. So if we're going to a lower temperature, we know that the vapor pressure is going to have to be less than 1 atmosphere. So we can at least eliminate choice E right off the bat because that one's greater than 1 atmosphere. There's no way that would ever happen. But we do have to do the mathematics now to get actually which of these numbers that's left is going to be the right answer. So the equation that relates vapor pressure and temperature is sort of typically given as a ratio. So the natural log of the ratio of two vapor pressures is equal to the enthalpy of vaporization divided by the universal gas constant R, and then it's going to be, the temperature is going to be 1 over T2 minus 1 over T1. There's a couple different ways of writing this equation. I think this is the form that your book uses. It depends on whether you put the minus sign in here or out front. You either switch these two or leave them like this. So, but mathematically they're all equivalent, and this is the equation we want to think about. So in this problem, we're going to call P1 1 atmosphere, which occurs at a temperature T1 of minus 108 Celsius. And then our P2 is what we're solving for, the final vapor pressure at the new temperature, and the final temperature is minus 148 Celsius. All right, so those are our temperatures and pressures we're dealing with, so we can start putting numbers here. The natural log of 1 atmosphere is our P1, divided by our unknown P2. I'll just leave it as P2, don't need to change the name of the variable. Delta H of vaporization. So enthalpy of vaporization is 12.6 kilojoules per mole. R, which is given here and also on your periodic table, is 8.314 joules per kmol. So we do need to convert vaporization enthalpy to joules. So that's going to be 12,600 joules per kmol. Sorry, joules per mole, not kmol. Divided by R, which is a constant 8.314 joules per kmol. And then the two temperatures. T2 is the second temperature, minus 148. We do need to convert both of our temperatures into Kelvin, though. So 148 Celsius is 125 Kelvin, so we're going to put it in as 125 Kelvin. And then the first temperature, T1, is minus 108, which is 165 Kelvin. Alright, so numerically what we get is that the natural log of 1 atmosphere over P2, and then when we multiply these numbers out on the right side of the equation, we come up with 2.939. To undo the natural log, we use E, so we're going to go 1 atmosphere over P2 is equal to E to the 2.939, which is 18.9, which comes out then with P2 equal 0.053 atmospheres. Alright, so a very small vapor pressure at this lower temperature, so choice A here is going to be the correct one. Just by lowering the temperature 40 degrees Celsius, we have a huge drop in vapor pressure down to 0.053 atmospheres. Okay, so that's how we approach this one numerically. There's not going to be a ton of questions like that in the test, but using this equation could be something that comes up on the final as well. Alright, next one we're back to so a couple questions about unit cells. The next three here are going to deal with, again, cubic unit cells. So here we're giving you the unit cell diagram for zinc sulfide. Determine the empirical formula of the compound and how many empirical formulas are present in one unit cell respectively. So I think it's actually easier to answer this question in the opposite order. So let's first look at the unit cell that we have. So we have sulfur is in yellow here. Sulfur is in the face-centered cubic arrangement. So we see that we have 1 sulfur on each corner, and we also have 1 sulfur in the middle of each face. So in face-centered cubic, we have 8 corners that count as 1/8 each. We have 6 faces that count as a half each because they're shared by 2 unit cells. And so that means we have 4 sulfurs in the unit cell. And then if we look at the zinc atoms, we're told here, note, zinc ions are inside of the unit cell. These are in tetrahedral holes. Half of the tetrahedral holes are occupied for this structure. And these ones are completely inside the unit cell. So for zinc, we just have tetrahedral holes occupied. But even if we didn't realize that that's what those were called, there's 4 of them inside the unit cell. None of them are shared because they're all completely inside the cell. And so that means we also have 4 zincs. So that means the formula of our unit cell is ZN4S4, which means that the empirical formula is just ZNS. So we can get rid of A, B, and E. And then we have, it looks like 4 unit cells, because the total formula of the unit cell is ZN4S4. The empirical formula is ZNS, so the formula of the unit cell is 4 times. So we have 4 of those zinc sulfide empirical formulas in 1 unit cell. So the correct answer here would be choice E. The formula is ZNS. There's going to be 4 of them per unit cell because it's in total 4 zincs and 4 sulfurs in this cube that's drawn here. Okay. Next one here deals with an atom at the body center of a unit cell is shared equally between how many unit cells. So this is just dealing with the positions in a unit cell, and we have, again, a few possibilities here. So we have corners, faces, edges, and body center. So these are basically the 4 different places that we can put atoms in a cubic unit cell. The corners are shared by 8 unit cells. So when we stack these cubic unit cells all next to each other, the corner positions are shared by 8 neighboring cells. The faces are shared by 2 unit cells. And this comes out of the table in the notes, so again, this is helpful to know. Edges are shared by 4. As we stack the cells next to each other. But anything in the body center, whether it's directly in the center or, as we saw in the last problem, just at least inside the unit cell, even if it's not right in the middle, these are not shared at all. They just belong to that unit cell. So if we have an atom in the body center, it's not going to be shared, so it's only going to be shared between 1 unit cell, the one that it belongs to. So it occupies only the main cell, not its neighbors. That's true for any body center position. So the rest of these would only be true. 4, 2, and 8 would be possible answers if we were talking about either edges, faces, or corners, but if we're talking about a body center, it's not shared at all, so it just counts as 1 for that unit cell. Alright, and then the last one here again deals with nearest neighbors. So these are mainly just definition problems, and this hopefully gave you a better idea of some of the stuff we need to know for the final exam. So if we have a primitive cubic lattice, we want to know how many nearest neighbors it has. And this again deals with the concept of coordination number, which is number of nearest neighbors. In other words, the number of atoms in the structure that are surrounding a specific atom. So look at how many are closest to it in the structure. So if you have primitive cubic, body center cubic, and face center cubic, the number of this is not coordination atom, coordination number. I was trying to talk and write at the same time, which never goes well, as you guys know. Alright, so coordination number is different for these three different unit cell types. So the primitive cubic cell is a coordination number of 6, body center cubic coordination number of 8, face center cubic coordination of 12, and the packing efficiency increases as the coordination number increases as well. So again, this is just information straight out of the table in the notes that summarizes the different unit cells that we want you to know for the exam. So the coordination number or number of nearest neighbors for a primitive cubic is going to be 6. So that's the answer we want to pick here. Alright, the last three questions here deal with phase diagrams. We had several questions on phase diagrams on this homework assignment. Generally, we did pretty well on them, so I'm not too concerned about our knowledge on these ones, but I do want to go over a couple of the different question types. So here we have a phase diagram for some fictitious compound Y, and we want to know what the normal melting point is. So remember, for a phase diagram, the first thing we want to think about is whether we, which regions are solid, liquid, and gas. So all the way to the left we have solid, all the way to the right we have gas, the middle region is going to be liquid. So this is the solid, liquid, and gas line for these molecules, regions for this molecule, and here we're looking for the normal melting point. So when we say normal melting point, that means two things. One is that the pressure is 1 atmosphere. So anytime we say normal, whether it be melting point, boiling point, or sublimation point, if that's appropriate, we're talking about a pressure of 1 atmosphere. And then we're also talking about the transition between solid and liquid. Okay, because remember, melting is referring to that phase change there, solid to liquid. So if we go to 1 atmosphere, we want to find basically this is the solid liquid line here, the line that divides the two, and we want to find what temperature this intersects with 1 atmosphere. So if we go over 1 atmosphere, we get to this point here, and then when we extrapolate down to temperature, it looks like it's clearly below 20 degrees Celsius. So the answer that makes the most sense here would be 18 Celsius. We also gave you 21 as the answer choice, but I think it's fairly clear from this diagram, hopefully it was on your computer screen as well, that the melting point here is below 20 degrees Celsius, so 18 is the only one that makes sense. So again, we go to 1 atmosphere, we go over to where it intersects the solid liquid line, and then we drop down and figure out what temperature that is. That's going to be the normal melting point of our substance. If we wanted the normal boiling point, we would follow this 1 atmosphere line over to the liquid gas line, and so the normal boiling point would be somewhere around 47. I think a lot of us picked 47 degrees Celsius as the answer. That would be the boiling point because that's the transition between liquid and gas, but the melting point comes earlier. It's the solid to liquid transition at 18 degrees Celsius. Alright, and then the next two questions deal with this same phase diagram that I have here. We want to know which corresponds to the equilibrium conditions between solid and liquid. So again, if we say equilibrium, that means 2 or more phases exist at the same time. And so you must be on a phase change line. So if we look at this diagram here, points like A, H, and C that are off of the lines, those are points where only one phase is going to exist at equilibrium. But if we're anywhere on the line, that's where we're going to have 2 phases in equilibrium. So again, we have to label the phases. We have solid, liquid, and gas over here, and we're looking for where solid and liquid can interact. So that's going to be on the line that separates the two, which is this line here. And so the only point on that line is going to be choice E. That's the one we can pick. Some of us may have been tempted to pick choice B, but choice B here is the triple point. So E is going to be on the solid liquid line, so that's going to be our answer. Choice B is what we call the triple point, and because that's where all 3 of the lines intersect, that's the point where all 3 phases can exist at equilibrium. So the triple point, you'd have solid, liquid, and gas. We're looking for just equilibrium between solid and liquid, which is going to be E here, where the dividing line between those 2 phases. Alright, and then the last question here, consider the phase diagram, same one. The letters denote specific points. The transition from D to C, we're talking about whether it requires what change in temperature and pressure. So we're going from D here down to C, and what you can see is that temperature is on the x-axis. So to go from D to C, we have to move right to left, That's going to be decreasing temperature, if it lets me write again. Come on. Alright, so D to C, we're moving right to left, so that's going to be decreasing temperature. And then we're also moving top to bottom, so that's going to be decreasing pressure as well. So to get from here to here, we go to the left and down, so we're decreasing both temperature and pressure. And so the one that works is choice B here, the pressure to decrease and the temperature to decrease and the pressure to decrease. Alright, that takes us to the end of this review, and I guess all the homework reviews for the whole semester have now concluded. As usual, invitation is open. Please come find me with any other questions you have, or if any of these still don't make sense after I went through them. I welcome you to ask any other questions, either by email or in person. I wish you the best on your final exams this week, and please know that I'm available to answer any questions you have about the exam or about the grading in this course, whatever comes up in the next week or so. Please let me know. All right, I'll see you in class for the last lecture later today.